This is the 28th lecture of the course MTH 204A for section B. Recall that in the previous lecture we proved Hilbert's Nullstellensatz, which says that for any natural number n, if we take the polynomial ring with n variables over the field C, then the maximal ideals of the polynomial ring are in one-to-one correspondence with the points of the complex n space. Okay. As I have already said that this is this Hilbert's Nullstellensatz provides us with a very important link between algebra and geometry. We will see an application for that. We will see that how by means of Nullstellensatz algebraic varieties and the maximal ideals of the quotient rings are related. Okay. In fact, that is the Hilbert Nullstellensatz is thus the gateway of the study of algebraic varieties, this is the algebraic varieties. These are the contents of the analysis of this algebraic varieties are done in the branch called algebraic geometry. So, Hilbert's Nullstellensatz is basically the gateway for algebraic geometry. Anyway, but I am not going to do any algebraic geometry here. I just did a Hilbert's Nullstellensatz just to as it is something, as it says something about maximal ideals. Okay. Well, so let me just do the definition that for simplicity let us keep the field to be C, and we consider the polynomial ring x1 up to xn. So, suppose we have f1 up to fr all belonging to this polynomial ring. So, okay, before that let me recall for you that if f is in an polynomial in n variables, then by 0 of f, maybe I should write I should quickly write that 0 of f is basically the set of all points such that f of a is 0. Okay. So, this is what called the 0 set of the 0 set, or loosely speaking zeros of the polynomial f. Okay. So, we loosely write this as f equals to 0. So, remember this actually, by this we actually mean this set. Okay. So, now take any finite collection of polynomials in this polynomial ring and we look at its common zeros. Okay. So, a subset of Cn obtained in this manner, that is a subset of Cn which is obtained in this manner, that is for some finite collection of polynomials in n variables, the given subset is the set of common zeros. Then a subset obtained by this is called an algebraic set or algebraic variety or simply variety. Okay. So, variety is an algebraic variety in Cn, I should say where it is in Cn is by definition is the set of common zeros of a finite collection of polynomials. Polynomial okay. So, this is the definition of algebraic variety. Sometimes we simply say variety. So, what is this? This is nothing but is a common zeros of a set of finitely many polynomials. So, let me give you some examples. So, what are the examples of varieties? So, maybe just quick quick examples. So, first of all, in any given point, let us say a1 up to an is a variety. Why? if you take this set of polynomials x1 minus a1, xn minus an, for this set the common 0. So, the common zeros for this polynomials is exactly this point. Okay. Another extreme case, if the 0 polynomial, so the 0 polynomial, if I take the 0 polynomial, then what are its zeros, right. So, any point in Cn will trivially satisfies this. So, therefore, that shows Cn is another example, Cn itself is a variety. Third example, quite easy to see, maybe third example, let us take a line ax plus by plus cz, ax plus by plus cz equals to, well, maybe the line means just c. So, this is also you can immediately see, this is the 0 set of first degree polynomial. So, therefore, any line in C2, so complex 2 dimensional space is also variety. Then of course, we do have other such things, for example, let us say z square plus omega square equals to 1, this is also trivially a variety. Then what more? I can okay, let me give an example of somewhat different example from somewhere else. So, recall that M and C is naturally identified with Cn square, right. So, this identification we have used several times earlier. So, therefore, and in view of this identification, now we are able to view every matrix as a point in Cn square. So, therefore, now we can, okay, for simplicity let us take 2, you will understand what I mean, and the general case goes exactly in this manner. So, what is the identification here? A, B, C, D, this is being mapped to A, B, C, D. If this matrix lies in SL2, then that means we must have AD minus BC equals to 1. So, therefore, you see if this is my polynomial x1 x4 minus x2 x3 minus 1. So, if I consider this polynomial, then the zeros of this polynomial they naturally get identified with SL2C. So, thus in this way we can perceive SL2C as a variety. Okay. Well, so several examples of variety has been given. Now, let me come to the main point. So, let me I can record it as a proposition. So, let V be a variety. Let V be a variety. Okay, maybe I should rather do the opposite one. So, let I be an ideal, which is finitely generated. Well, later on we see that actually we do not need to write down the conditions finitely generated, because every ideal of this polynomial will be automatically finitely generated, but those things we will prove later. So, until we prove that, let us mention this, that we are considering finitely generated ideals. Let me again repeat. So, I am saying that every ideal of this ring is automatically finitely generated, you do not have to mention that, we will see later, but until that point let us mention that all the ideals that we are going to consider are finitely generated, say okay. So, we take a finitely generated ideal of this polynomial ring, let V be the variety defined by the common zeros of those polynomials. Okay. Now, in one hand, so for example, let us say if my ideal is generated by a single point, sorry, if my ideal okay. So if this is if these are my functions, then the variety is going to be this point, and if I take let us say the trivial ideal, then V is going to be whole Cn. Okay. So yeah, then in one hand I have the maximal ideals of this polynomial ring, quotient ring actually, are in one-to-one correspondence with the points in V. Okay. So this is what we will prove now. So try to see that look at this very simple extreme case that if I is trivial, then V is going to be whole C. So therefore then this is nothing but the statement of Hilbert's Nullstellensatz. Okay. So thus you can see that using Nullstellensatz, I mean this you may regard as some extension of Nullstellensatz. But however, the thing is, like in view of this proposition, one can now think every point of this V as a maximal ideal in this quotient ring and vice versa. Okay, let me do the proof here. Proof is indeed quite straightforward. So by means of the correspondence theorem, it is clear that every maximal ideal of this quotient ring is nothing but a maximal ideal of the original polynomial ring containing I. Okay. So what I am saying is maximal ideals. So this is just the correspondence theorem which we have proved earlier. Are in bijective correspondence maximal ideals of C of x1 up to xn containing okay, just you have this quotient homomorphism whose kernel is I. So therefore now the maximal ideals of this quotient ring will simply move ourselves to this collection, that is the maximal ideals of Cxn containing I. Now try to understand, so here any maximal ideal will look like A, some M A for some point A, right, and this maximal ideal is containing I. Then what does that mean? So is containing I means, so all this f1 up to fr will be contained inside this maximal ideal. Okay. So yeah, so what it means is, it immediately follows, because MA is the kernel of the substitution map. So therefore it immediately follows that f1 up to fr A all have to be 0. Therefore this shows, and this is if and only if, so all these states are if and only if A is in V. So in view of Nullstellensatz, we see that now the theorem is thus proved. Okay. And another important and immediate corollary of this is the following. So before, okay, let me just before that tell you some, okay, let me put it as a remark. So as like earlier, I take R to be commutative ring and maybe I is an ideal. Okay. So I mean what I have just said here, So, that is in fact I mean it holds in the generality as well. So, because ideals, we have ideals one to one correspondence between ideals of R containing I ideals of R modulo I, and this bijection preserves inclusion. So, in view of this, it is quite clear that, like for example, if R modulo I is if so if I is whole of R, then this is going to be a trivial ring. So, then it has only trivial ideal, and on this side you see that R is the only ideal containing I. Okay. So, the point that follows from here is the following, that there exists a maximal ideal of R containing I. How? So, the maximal ideals here and the maximal ideals here is one to one correspondence. Okay. So, therefore, and now remember that R modulo I is also a ring, commutative ring. So, therefore, it will have a maximal ideal. So, therefore, like in view of the existence of maximal ideal for any commutative ring and this correspondence theorem, we also derive that given any proper ideal, of course. So, as a proper ideal I should take, okay, otherwise it does not make sense to talk about maximal ideals. I is a proper ideal, yeah, I is assumed to be a proper ideal. So, if I is trivial, then the statement is obvious. So, yeah, since we do have this is a I is proper, so this is not a trivial ring, so it contains a maximal ideal, and then pulling it back you get a maximal ideal containing I. Okay. So, not only every commutative ring has a maximal ideal, also if you give any proper ideal, that is going to be contained in some maximal ideal. That is what we have learned. And now, an immediate corollary to the above proposition is the following. So, what is that? So, suppose I am given with a collection of polynomials having no common 0. Okay. Then there exist polynomials GR such that 1 or equivalently is whole of the polynomial ring. Okay. So, the equivalence of last these two is actually quite clear, because any ideal a typical element of this ideal is the typical element of this ideal is of the form of some such form like this. So, yeah. So, therefore, if one can be written as a combination of them, then that means this ideal has to be the whole of the whole ring. So, the equivalence of this and this is okay. Now, why the statement is true? So, like we will prove that it is better to prove that this ideal is exactly equal to the whole ring. If not, then this will be contained in a maximal ideal of. So, assume contrary. Then there is a maximal ideal maximal ideal such that all of them lie in this maximal ideal. And again, so there is a maximal ideal containing, maximal ideal, okay, that is there. There is a maximal ideal containing them. Now, since there is a maximal ideal containing them, therefore, the variety defined by this set of polynomials cannot be empty, right. The variety cannot be empty, and that is a contradiction, because we have assumed there is no common 0. So, like so in view of this Hilbert's Nullstellensatz, or this is now done, but without using any connection with Nullstellensatz, I mean it is somewhat not so obvious, because in one end it says it is having zeros on okay, just a minute. Of course, if this holds, then there cannot be any common 0. So, the main part is actually the opposite one that we have stated here, if there is no common 0. So, basically given a set of polynomials, and this is a very geometric property that it is not, it is not giving any non-empty variety, and from that we are concluding that the ideal is the whole of the polynomial ring. Okay. So, I think now we can stop this discussion on maximal ideals and do something else. Maybe we should do division and factorization in general integral domains. Okay. So, therefore, division and factorization. So, we are already familiar with these two words, these two words division, factorization. We are already familiar with these two words, but in the context of integers, like we have performed divisions of integers, factorization of integers. Okay. So, in this lecture what we will be doing is we will be we will be talking about divisions and factorizations in more general commutative rings. So, our investigation will be modeled on the basic properties of integers. So, we first review those basic properties of integers, and then we will formulate and establish those facts in the more general setting. So, let me first do that. So, as I said that I will start with reviewing, I will start this discussion by reviewing the basic properties of integers. If you remember and note, if you have observed carefully, then you can see that if you have observed carefully, then you might have you must have noted that many things that we prove regarding integers, of course related to division and factorization, many of them they are direct, or they are either immediate consequences of the division algorithm, or they are the immediate consequences of something which are indeed the consequences of division algorithm. So, the point that I want to make is, many things that we do in case of integers, they follow from division algorithm. So, what was division algorithm? Let me quickly recall for you that suppose a and b are two integers. Let me take a not equal to 0, then there exist integers q and r such that b equal to aq plus r, where r is greater or equal to 0 or less than mod a. This is called the division algorithm. Okay. and this integer, and this, in this case it happens to be unique, but right now I am not so much bothered about uniqueness of quotient and remainder. And what are the important consequences of this division algorithm? So, let me write down one by another. So, Z is, so every ideal of Z is principal. Every ideal in Z is principal. Okay. Then given any two integers, not both 0, there is a GCD. So, what is a GCD? There is a integer Z D such that, so one of them is of course D divides both A and B, and if E divides both A and B, then E must divide B, E must divide D, right. Okay. Well, traditionally we assume D to be the positive one, right. Traditionally we assume D to be positive, and in that case you can simply, you will obtain that E is less or equal to D. But again, since in RBA we want to, as I said, that we want to develop these facts and in the more general setting where there is no notion of small positive or negative. So, therefore, here therefore, while writing this I do not insist that D has to be positive, because that is not the that is not the main thing. The main thing is D is something that divides both of them and then this. Okay. And also then we do have another property regarding D is also, let me directly write. So, it is of the form that Ax plus By for integers x and y. Okay. Then what are other things we have seen? So, suppose P is a prime, and P divides A and B, that should imply P divides A and P divides B, or P divides B. Okay. Let me just separate it out here. This is also another thing. Then perhaps the most important consequence, where everything culminates to, is fundamental theorem of arithmetic. Fundamental theorem. Okay. So, these are, so these 4 or 5 things are therefore actually follow from the division algorithm almost directly. Okay. So, now what is our aim? Our aim is to establish these facts in the much more general setting. So, the question that we can naturally ask here is, like, first of all, can we extend or can we generalize the this results, or in fact to begin with the notion of division, everything. So, well, let me put it here. So, these are the 5 theorems I will be focusing on. So, the question which I would like to ask is, can we establish or can we generalize this 5 results in the setting of any general ring? Actually, that is not quite true. I will give you an example, and then of course, the extreme one, that, well, for Z we have seen these 5 facts. So, do we really have a ring other than Z where we can also have the versions of these 5 results? This actually we have. For example, take F to be any field and consider this polynomial ring Fx. Then for polynomial also we have already proved that any ideal of Fx is also principal. Then for polynomial we do have a notion of their greatest common divisor, and similarly this is also, I mean, till fundamental theorem we can also have for polynomial, have for one variable polynomial rings. So that is, this is one example of a ring, of course other than Z, where we do have all these 5 results. And let me also now tell you that another the opposite scenario, Zx in Zx 2 and x, these 2 polynomials, they have GCD 1, right. I mean, there is no polynomial that divides both of them, dividing inside Zx, but however, so their GCD is 1, however 1 cannot be written as some polynomial times 2 plus some polynomial times x, 1 cannot be written. So, like here we obtain a setup where this one does not hold. In fact, the scenario is there are relatively few rings for which one can extend, to which one can extend all these 5 results. There are only relatively a few rings. Okay. So, and we have also already seen some I would say very common ring where we cannot even expect this. Okay. So, in this lecture and onwards, at least for some for next few lectures, our aim is to consider those rings. We would aim to consider those rings where we can generalize all this. We can generalize this this 5 phenomena. Okay. All right. So, I think I have made my aim clear. Now, before I go ahead, let me introduce some terminologies which we will be using from now on. So, the first is the notion A divides B. So, what it means is, okay, so our setup is, I will from now onwards I will take R to be an integral domain. So, by an integral domain, let me remind you, it is a commutative ring with unity and there is no 0 divisor, and since there is no 0 divisor, so therefore it has the property called cancellation laws. That is, if AB equal to AC, then from that it follows, and A non-zero, then from that it follows that B equal to C. Okay. So, now let me introduce the terminologies. So, this means A equal to BQ, okay. No, A divides B, so it should be rather B equal to AQ for some Q in R. Okay. So, then we say that A is a divisor of B. Next thing that we are going to call is proper divisor. So, A is a proper divisor of B. Okay. So, before that, let me equivalently put in this in terms of ideals. So, equivalently, ideal generated by B is contained inside ideal generated by A. Okay. Now, we call proper divisor. A is a proper divisor of B. What it means is, of course, A has to be a divisor of B, but here proper means neither A nor Q is unit. Okay. So, in terms of ideals, so of course, this is what we have to happen. Okay. So, in terms of ideal, this is what it says. The third thing is associates. So, let us say A and B are associates, it means A divides B and B divides A. Okay. So, here A and B are arbitrary rings, and let us take n not equal to 0. So, and equivalently, if this is if and only if we can see that A must be of this form BQ, where Q is a unit. This is easy to see, and in terms of ideals, this is to be put as okay. So, the fourth terminology that I want to introduce is prime element, or maybe I should first do irreducibles. So, an element, of course, an element a non-unit. So, A is not an unit, assume we say A is irreducible, means it has no proper divisors. It has no proper divisors. It has no proper divisor. It has no proper divisor. Then, for example, then what does it say? Another way to put it is the following, that if A equal to BQ, then I mean they cannot be proper divisors, right. So, proper divisor means like B cannot be proper divisor. So, what are the I mean if something is not a proper divisor, then what are the possibilities? So, proper divisor, for a proper divisor, remind that note that I mean if A is a proper divisor, then A cannot be unit and Q also cannot be unit. So, therefore, here it immediately says that one of B and Q must be a unit. Okay. So, therefore, it in other words the only divisors of A are the units and associates. Okay. Yeah, so the only divisors of A are units and associates. Next, we will define prime elements. Next, we define prime elements. What do you mean by a prime element? So, okay. Okay, before that I think I should write this in terms of ideals. In terms of ideals, if and only if. So, these verifications are quite obvious. There exists no principal ideal C such that the following happens. Okay. There is no principal ideal with this property, because since A is non-unit, so there certainly this has to be this principal ideal generally has to be a proper ideal. So, it says there is no principal ideal strictly in between them. Now, let us come to the prime element. Okay. So, let P in P be in R not an unit is said to be prime of course prime in that ring if okay, whenever P is dividing a product it must divide one of them or equivalently if the ideal generated by P is a prime ideal okay. Well, here I should make a comment that here till this point it was fine, but here I have defined two notions, one is called irreducible, another one is called prime, but in case of Z you see that what you have seen earlier, in case of Z they seem to be the same thing. So, the point is then why I have written them written them separately. The reason is that what you said is true that for in case of Z, I mean what you have seen is in case of Z they are immediate, they are of course same, but that is not the case in arbitrary for arbitrary integral domains. For arbitrary integral domains we have these two distinct notions. However, we will mostly deal with situations namely UFDs where this primes and irreducibles they are the same thing. In fact, like in any integral domain primes are always irreducibles. Let me directly give you a proof for that. I will give you examples. So, like if R is an integral domain, and A is and P is a prime, P is a prime, then R is an integral domain and P is a prime, then what happens is P is also irreducible. Giving a proof of this is not difficult. Let me prove it as a proposition. Suppose P equal to AB, you want to show P is irreducible, then that means if there is a factorization you have to prove that one of them must be unit, right. So, it immediately says that AB, so since P is prime, one or I mean either A or B will be divisible by P. So, why do not we just take let us say this one. So, P divides A or P divides B. So, assume P divides A. So, therefore, then what you have is P equal to some P times Q times B. We are working in integral domain. So, therefore, one must have. Okay. So, that shows that I mean B is an unit. Okay. What you want to show. So, in any integral domain primes are always irreducibles. Okay. But however, the converse is not true. We will see examples soon. So, since in arbitrary situations I mean these two notions do not exactly coincide, that is why we have separated them out as separate terminologies, but in case of Z or in fact in case of any later on we will show for any UFD irreducibles are also primes. Anyway, So, yeah. So, with this terminologies, let me start generalizing those five phenomena. So, one thing that we are convinced with is, if in our if in the given integral domain R, if we can somehow define a notion of if you can define a notion of division, like division means that you will have a quotient and a remainder. If we can make sense of division, then if it is done in a coherent and proper way, then we can expect that as a mere consequence, all those results that we are striving for will follow immediately. Okay. So, therefore, we should now think of the notion of division, or to be more precise, division algorithm in the setup of in the general setting. So, what is actually happening in division algorithm? We are given, let us say, two elements A and B. So, by A I am dividing B, I am performing the division, and then I am getting a remainder. Okay. And the important property of the remainder is that it has to be, let us say here, its size must be smaller than that of A. Okay. Another setting where, another ring where we have performed divisions earlier is ring of polynomials. There also fx equals to gx times qx plus rx, where degree of rx is strictly less than that of gx. So, the point that I want to make is, after division, the remainder that we want to obtain, that if that does not decrease, if its size does not decrease, then there is no point of carrying out a division. Okay. So, like whenever you want to, if you want to define division, this division process or division algorithm, whatever, in the general setting, then what we must do at first is, we have to define a size, or a notion of size of its non-zero elements. Okay. Because like otherwise we cannot make any sense of saying that the phrase that the remainder is the size of the remainder is decreasing, okay, which is actually necessary, otherwise there is no point of carrying out any division. So, therefore, let me make this definition. So, as I said, the building blocks for developing the general theory are these two prototypes of examples, namely ring of integers and ring of one variable, ring of polynomials in one variable over fields. So, the striking similarity between them are now being generalized to a more general setting called Euclidean domains. So, let me write down the definition. So, as usual, R is an integral domain. Integral domain, it is said to be a Euclidean domain if there is a function which we will loosely refer to as the size function. So, it is a function from non-zero elements of R to non-negative integers, function satisfying the following, that is, for every A B in R with A non-zero, there exist Q and R in R such that B is equal to AQ plus R, and either R is 0 or the size of R is strictly less than that of A. Okay. So, if an integral domain has if integral domain for integral domain R, if there is a function such that there is a function that enables us to perform a division, then we will call that domain as a Euclidean domain. Okay. So, just to make sure that you have understood, let me tell you a few examples. So, the first example is of course Z, where the size function is simply absolute value. Okay. The second example must be another one which guided us to this definition Fx, where F is a field and sigma of F is nothing but degree of F. Okay. Third example. So, before that let me of course show you one thing, that let me make a remark that like in case in the division algorithm for Z or Fx, there we did have the uniqueness of quotient and remainder, but in this generality we don't insist that, because very soon we are going to encounter some common rings where we can have only existence, not uniqueness. Okay. Let me give you an example for that, that is better. So, the next example that we should consider is, let us say Zi, and what is the sigma here? Sigma of A plus IB is A square plus B square. So, let me work it out why this is. So, this is nothing but the square of the norm of the complex number and nothing else. So, why is this an Euclidean domain? Let me work it out. So, as expected, if I take two, okay, maybe first I will explain the things geometrically, that is better. So, let us draw the diagram. So, let this be the usual complex plane, then we first plot the points of Zi. So, the points of Zi, they are basically forming a lattice. Okay. These are my points. Okay. Now, if I take, let us say if I take a non-zero, let this be R. Okay. Let me rather write it alpha for simplicity. Then what is the principal ideal generated by alpha? So, this is by definition all multiples of So, how to visualize this principal ideal? So, write down alpha in its polar representation. Okay. So, now it means that whatever I am doing is every vector is now being rotated by an angle theta, and then it is staged by the factor r. So, therefore, so this is nothing but what we will do is we take every vector, we will rotate it by that appropriate angle and then scale it appropriately. That is how we are going to get the principal ideal generated by alpha. Okay. Now, if beta is another this Gaussian integer, so therefore, alpha might look like something like this. If this is my origin, alpha may look like something because it has been stretched out, alpha might look like something like this, and then apparently it will be there, then it will be there. So, basically some another larger grid that you will get, okay, something like this anyway, something like this. Now, why is differential algorithm true here? So, what we have to do, that means beta equal to write this as alpha times gamma plus some delta, where delta is either 0 or size of delta is smaller. So, what does that mean actually? So, geometrically can we see how to obtain this gamma? So, like let us suppose beta is somewhere here, then we see that there is at least one multiple. So, given beta somewhere, so it will be in one of these squares formed by translating alpha, right. It is one of these squares formed by this alpha, and geometrically we can see that, of course, we will be giving a rigorous proof that at least like given beta here, there is one multiple of alpha from which the distance of beta is the least one. That is geometrically clear, that is exactly going to be our gamma. So, now for a formal proof we do the following. So, this is just a geometrical visualization, that how to like it just tells you why the division algorithm is true here. Geometrically it is quite clear that there is a point which is there is a point in the lattice generated by alpha which is closed to this, which is the closest one from this beta. Okay. All right. So, let me do it here. So, therefore, suppose a plus I beta, yes, let me call it alpha not equal to 0, and beta c plus I d, I would like to produce a gamma. So, how to do that? So, geometrically we have an idea how to tackle, algebraically the proof runs as follows. So, for simplicity let me now consider them as complex numbers, and first consider the quotient inside C. Okay. Consider the quotient inside C. I would like to do the following, because like the reason for that is, so we are taking the advantage of the existence of a field which is containing this as the subring, because if at all this is to happen, then one must have, okay. So, therefore, this gamma must have something to do with the quantity with this complex number. So, keeping that as a motivation, let me consider the quotient here. Remember, here I am just like this is a complex number, is not necessarily a Gaussian integer. So, we divide them as complex numbers, because in field we can always do, and whatever we obtain there, from that we will pick up an appropriate Gaussian integer. That is what the idea is. Okay. So, C plus I d divided by a plus I b, let me write that as x plus I y. So, what is this? We can immediately do it. In the bottom we will have a square plus b square. So, C plus I d, a plus I b, therefore, a c minus b d, I should I think, so a c plus okay, so a c plus b d plus we must have a d minus b c, a square plus b square. Okay. So, therefore, we know what is going to be x and what is going to be y. So, next what we do is what we do here is the very common, very usual thing, that is given this x, there exists, we can pick up an integer u such that x minus c is less or equal to half. Okay. the reason for picking up this x and u is actually like it is motivated from this picture that given a point we are going to find out, we are going to pick up a lattice point which is closest to the given point. So, that is what exactly we are doing, and this is nothing but very simple thing that if like for given x the greatest integer less or equal to x and something added to that, one of them must have at a distance less or equal to half. Okay. So, similarly we have y minus v, and then the rest we know what to do, that take gamma to be. So, u plus I v. Now, we just have to show that it is just left to show that beta minus alpha gamma, it has the proper size. So, what is this? Let me simply write it. So, there beta is of course okay. So, this is what is beta by alpha, right, beta by alpha. So, beta equal to alpha times, so alpha times x plus I y minus alpha times u plus I v. So, therefore, this everything is alpha into x minus u, alpha into x minus u plus I into u minus v, right. Now, sigma of this quantity is nothing but, so it is a norm square. So, nothing but, so sigma of this quantity will be sigma of alpha times sigma of this. So, then we can do it immediately here. What is the sigma of this quantity? So, sigma of x minus u plus y minus v, the way sigma is defined, x minus u whole square plus y minus v square, and this is nothing but 1 4 plus 1 4 equal to half. Okay. So, therefore, the entire thing is basically sigma alpha times half, and that is exact, and that is how we are done, because the sigma of this is half of sigma of alpha, that is strictly less than sigma of alpha. So, therefore, by explicit computation we see that this is also going to be a Euclidean domain. Another example along this line is the following. In fact, we will generalize that. So, this takes z root 2. So, what is the, how is the sigma defined there? This is simply a square minus 2b square. Okay. So, here also I mean I leave the rest of, I leave the proof before you. So, to you, so the strategy is exactly simple. So, you take two elements alpha and beta, and first you perform the you consider the quotient inside R, and from there you pick up suitable suitable elements from this ring. Even more generally, if D is square free, and then Z root D is an Euclidean domain, okay, where of course sigma of A plus sigma will be exactly like this. So, maybe I am leaving this to you. A plus so square of integer A plus B root D is nothing but A square minus D B square. Okay. So, more generally this is the case. So, some quick examples, or standard examples of Euclidean domain are given. Now, let me prove, as I said, that my aim is to prove those 5 phenomenon in this setting. So, let me get into them one by one. So, since by definition in Euclidean domain, okay, so before that let me also make a remark that let us say in this situation Z I, you see that the remainder cannot be unique. Okay, so because there could be multiple choices for the remainder, multiple choices could be there, the number of choices of course at most 4, but the thing is that always we cannot expect the uniqueness. Okay. So, this is a setup where like everything till the existence that goes, and we can immediately generalize, but when it comes to the uniqueness certainly we cannot expect that. Okay. So, that is why while considering general Euclidean domain we did not insist that the remainder has to be unique, because that is actually, this happens to be very very restrictive. There are interesting rings where things go completely nice except the uniqueness. Okay. All right. So, I think with this I will finish. R is an Euclidean domain. R is a PID. So, what is PID? Principal ideal domain. That means every ideal is a principal ideal. R is a PID. So, what are the example? Let me give a quick proof. Let me give a quick proof for that. So, actually, so let I be an ideal. If I is 0, then actually we do not have to do anything. Now, consider that I is a non-zero ideal. What is a non-zero ideal? So, I mean here if you will immediately see that okay, before writing down the proof, let me tell you the idea that if you have if you for okay, so if you can remember that the proofs of the facts that in both in Z and in case of polynomial rings, why every ideal in either of these two rings every ideal is principal, if you look at their proofs, you see the proof is very similar. Okay. In case of Z, you take the you take the least positive non-negative integer lying in that ideal. In case of polynomial rings, you take the polynomial lying in that ideal with least degree. Okay. So, the proofs are exactly similar, and the reason for being the proofs are exactly similar is this, that both of them are the special cases of we can review their proofs in this more general scenario. So, because now you know that both this degree or the absolute value, both of them are special cases of the size function. So, therefore, the proof in the general case should be the following. What we will do is we consider sigma of A belonging to I not equal to 0. So, since this I is non-trivial, so this is going to be a non-empty subset of non-negative integers. By well ordering, we do have let us say we do have a alpha belonging to this with sigma alpha least. Okay. So, we do have an alpha here where the minimum attains, and then like earlier we will show that this alpha generates this whole of I. And that proof is also quite obvious, that first of all, since alpha, okay, so there exists alpha in I not equal to 0 such that this is the list. So, since alpha is in I, so ideal generated by alpha is contained inside I. Now, to see the opposite direction, what we have to do is very simple. Let us take beta in I. So, since we are working in a Euclidean domain, there exists gamma such that alpha gamma beta minus alpha gamma is either 0 or right. Now, you see that if this quantity is non-zero, so this quantity also lies in I. Therefore, inside I, if this is non-zero, inside I you will have a non-zero member whose size is getting small, whose size is smaller than that of alpha, but by my choice that is not possible. So, therefore, this is this must be 0. Okay. So, that finishes the proof that every Euclidean domain is a principal ideal domain. Okay. So, that is this collection of principal ideal domains is like it's a larger collection to that of collection of all Euclidean domains. So, those properties that we are talking about there, those properties now we are going to see in the setup of any PID, and then we will further generalize as much as possible that to to another more general setting called unifactorization domain or UFD. Yeah. So, I think for today it is enough. So, the main point that we want to emphasize is earlier the striking similarities that we have observed between Z and Fx, the similar though the striking similarities led us to a general setting of which both of them will be just trivial, with just special cases, namely such a setup is something called Euclidean domain, and the proofs also in the earlier cases were similar, because the general proof, because you see that this general proof, the proofs in earlier the proofs that we have seen in the special cases are simply obtained by specializing the general proof to those setups. So, basically their proofs had now been culminated to the proof in, we reviewed the proofs, and that is how we culminate them culminate them to a proof of the analog in this proof of that appropriate analog, or the general proof of the generalized so proof of the generalization in this setting. Anyway, so I will stop.